Okay, so in this case, we've got 4 questions. So a small pebble of mass 500 grams is attached to the lower end of a light string. Find the tension in the string, and then there are 4 scenarios with different types of acceleration. So I've drawn the 4 diagrams because they're all a pebble of 500 grams, so that's 0.5 kilograms. So the downward force from the pebble is 0.5 G. There is a tension in the string. It says the string's light, so there's no weight in the string, so that's not going to have any effect on it. So there is a tension in the string which is acting upwards on the pebble. So in each of the scenarios we have the same situation: 0.5 G acting down, tension acting up, and in each case we need to find the tension given different accelerations. So what I'm going to do in each case, I'm going to write the acceleration against each diagram. So the first one is moving upwards with an acceleration of 2 meters per second squared. So that is the notation I'm going to use for acceleration, and I'm going to apply Newton's second law in an upwards direction. So I've got T minus 0.5 G equals mass, which is 0.5 kilograms times 2. So T is equal to 1 plus 0.5 times 9.8. I think I could probably do that one, but let's make sure we don't make a mistake. So I end up with 5.9 newtons. Okay, now the second one, and we'll see this is all about getting the acceleration right, is moving downwards with an acceleration of 3 meters per second squared. So I'm going to just draw it onto my diagram, 3 meters per second squared, and this time I'm going to do F equals ma in the downward direction. 0.5 G minus T equals 0.5 times 3. So T is equal to 0.5 times 9.8 minus 0.5 times 3. And the answer is 3.4 newtons. Okay, so the third one. So this time, so we need to be quite careful here. It's moving downwards at a constant speed of 5 meters per second. So this time there is no acceleration because it's a constant speed. So actually these two things are equal. So if I can think of it as F equals ma with a 0 acceleration, or I can just think of the whole system is in equilibrium. There is no change in velocity, so the acceleration is 0. So T equals 0.5 G, T equals 0.5 times 9.8, which equals 4.9 newtons. Okay. Okay, so the fourth one. This is now moving downwards with a deceleration of 4 meters per second squared. Now I have two options here. I can either say this is acting down with deceleration, so it's accelerating downwards with an acceleration of -4, or I can say that it is accelerating, even though it is moving down, the acceleration is up. So I can do either of those things are going to work. So I'm going to take this one here. I'm going to use that there because I prefer to use positive values. So I'm going to resolve up. I'm going to do Newton's second law, T minus 0.5 G equals 0.5 times 4. So T equals 0.5 times 4 is 2 plus 0.5 times 9.8. I think I'll just do this without typing it in the calculator. 0.5 times 9.8 is 4.9 plus 2, so that's 6.9 newtons. Okay, so as you can see, the complications came into these bottom two, and just in being really careful with the word in the question and interpreting it to ensure you've got the acceleration of the right value, and more particularly acting in the right direction.